So, I've been in UCLA for 1 year. I guess this is the heaviest ring I ever see, so you guys are lucky. So first I introduce myself. So I graduated from MIT in 2018. So after that, I joined the Chinese University of Hong Kong as an assistant professor there. After 3 years, I decided to move. So I relocate back to United States and joined UCLA early last year. So I've been here for almost a little bit more than 1 year. So I've been doing research on this interpretability and deep learning for some time, mainly from the perspective of computer vision researchers. So I've been done many work building this visual recognition database, such as Places, AD20K for visual scene understanding, to this like network dissection, policy dissection that try to understand and visualize what's going on inside the deep representations. So today I would like to give you a brief summary and also the transition from the earliest work I done from network dissection that try to look into the deep representation trained for classification to this policy dissection or GAN dissection that our recent work that try to look into the deep representation trained for other tasks such as image generation as well as some reinforcement learning representations. Try to understand what have been learned inside those deep representations. So recent years, we see many amazing progress by deep neural networks, right? So we have the neural networks such as ResNet that can classify image at a human level. So giving this image, recognize this is a convention center. And also, we have representations that can synthesize photorealistic images, such as GAN and the recent diffusion model, right? So giving some latent vectors, so can generate such realistic images. We also have the amazing models such as AlphaGo that can train from self-replay, then that can outperform the best Go players in those very complex strategic games. Also, the neural network being used in many machine autonomy applications, such as maneuvering those vehicles. So they show that AI beats the human F-16 pilots in a Department of Defense event. So people developed all kinds of crazy architectures. If you take a look at the recent machine learning conferences, a lot of different architectures have been developed. So in computer vision, we have the ResNet, which have hundreds of layers, also master with different structures, also have this random network that try to eliminate the architecture priors, try to automatically learn the structures. Also in the domain of natural language processing, so we have this gigantic model such as GPT-3, take months or hundreds of GPUs to train and also achieve human level understanding on the text. The recent chat GPT, which built on GPT-3 from OpenAI, uses human level reasoning and question answering. Also in speech, we developed this kind of recursive neural network that can process speech and signals and then generate realistic speech that can even help you order food from the restaurant. Before we are too excited about the progress of deep neural networks, I would like to take a pause and take a look at history. One of the founding fathers for artificial intelligence, Alan Turing, once proposed this very important question more than 50 years ago in this influential paper. So he proposed questions, so can machines think? So this is a very fundamental question, right? So can machines think? So he said its definition should be boiling down to two parts. One is the word machine, and another word is the think. Machine right now we can interpret as this data-driven AI models that can crunch on a lot of data, then reach this human-level performance. Then the think. Here there is the underlying assumption for the think word, I think. The underlying assumption here is a machine should think like us human, right? So we build such models. It's reach human level performance. So presumably it think like this machine should think like us humans which means shouldn't think like a fish or sponge, should think as humans. But are we really getting there to answer the question, the machine think like a human? We still have a long distance, right? So if we show this machine learning models to Alan Turing, if you can come to our symposium and we show Alan Turing all those crazy network and machines, so probably he will be really sad about this, so puzzled about seeing all these crazy large models. So we still don't answer the question whether this machine or data-driven machine AI models can think as a human, right? So we put this data-driven neural network here. So basically, it's connections, a lot of millions of connections, and the weights can learn from the data. So we have the input and the output. So when we try to answer the question, can machines think? What we really try to answer is how we humans can understand their thinking process, their internals, right? So we want to look into their deep representation, see how they do the processing, how they can process the raw input and generate the meaningful outputs. So that it's related to the discovery of AI knowledge, right? So we train this model to solve a lot of domain tasks, like how to recognize image, how to generate image, and how to maneuver the vehicles. So train from the pure data-driven way. So we have the representations. On the other hand, we also have the human domain knowledge, right? So we human develop a knowledge base, then we teach our kids to do those tasks. So we have the human domain knowledge, so there will be some overlap between the two. So that will be the crux for our problem. So we try to discover the interpretable neural knowledge that have overlap between the AI knowledge and the human domain knowledge. But I have to say that for the non-overlapped part, it's also very interesting. It means this AI model can discover some new knowledge, like a new knowledge frontier. If we can do that, we can even expand the horizon for our human knowledge. So we will talk about later. But this talk I will focus on how can we discover the overlapped and the interpretable neural knowledge. So I will talk about different deep representation built for different tasks and try to visualize and interpret what have been learned inside. So I will start from the deep representation trained for image classification. Then we'll move into the deep representation trained for the image classification, right? So it's an opposite task for image classification. So giving a random vector, so generate a realistic image. So we try to understand what have been learned inside this deep generative representation. Lastly, then we'll talk about the knowledge learned inside the deep representation for this from reinforcement learning, like for this local motion task, and see how this internal representation learns this motion primitives that can help do the decision makings to help this robot navigate. So let's start with the easiest one, the deep representation for image classification, and look into zero knowledge representations. Because I work in computer vision, right? So over the recent 5 years, if you take a look at the computer vision conference, so more than 90% of papers about deep learning, right? So people build deep neural network to do image classification. So here is one of the earliest model I built for the scene classification. So we collect this large data set, have 10 million images for scene understanding. Then we build a scene classification models. So given the input image, we put 72% in the booth. And if you're giving another image, some image of me on the beach, then it recognize 62% beach, so very accurate. So we also can parse another image. So here's another image of my friend. It's fit into the neural networks, then give me a little bit bizarre prediction, 95% martial art gym. So I'm pretty sure my friend don't know any kung fu, right? But why this give me this prediction martial art gym? Can anyone give me some guess? So why this model give us this prediction? Any guess? Yeah. Fit? Yeah. Yeah, so that's a very interesting property, right? So giving some bizarre prediction of the neural network, why this model give us this prediction? So we try to understand their internal and reasonings. So it's indeed, so we build some Sine state-based method. It highlights the bare feet as a most informative region to predict this martial art gym. So nor such bare feet are most reasonable evidence to predict the class. But why this can give us this prediction? So we want to look into their internals. One popular approach is a data-driven approach to visualize what's going on there, right? So we can just take a lot of images and feed a lot of images into the representation and probing their activations and correlates their activations with the input image. But if the images is not annotated, then the value is very low. So to change that, so we develop some method, more principled method called network dissection that try to probing the deep representations with a visual knowledge base, right? So in computer vision, so we build a lot of annotated database. So we just collect all those database together, annotated with all kinds of concepts, such as this color concept, also this texture and surface concept. We also have the food and object parts annotations. So we can feed those images with annotation into the deep representation and observe how the internal units. So here I consider each convolution filters as the unit we try to visualize and analyze. So we can actually identify the top activated regions along those images. Because those images are fully annotated at the pixel level, then we can not only generate those top activated images, we can also associate labels, the most confident labels from our visual knowledge base for each one of the concepts. So here I show you two units. So one is annotated as a lamp. So you can see it's consistently activated by the lamp region. Also, we can associate a score, quantitative score, to measure how this label quantitatively associated with this concept. So basically, we use intersection over union to calculate this detected region. So it have a 0.34. So here is a second unit. So this annotation is a face neuron. So it's consistently activated by the face. This is with an IOU 0.53. So based on this kind of network dissection, so we can apply to many trained neural networks. So we apply this network dissection to a model trained for scene classification. So we figure out that a lot of the internal units emerge as object detectors when trained from scene classification. So this result is very interesting because we train this neural network with the labels of scenes, right? So the living room, kitchens, bedrooms. So we don't have label of object categories, right? So the object detector are more like an emergent detector that try to solve the final scene classification task. So I will call them like emergent detectors. This is interesting because we human doing things like this, right? So we recognize this is the auditorium because we see chair and people. We recognize that is a living room because there's a sofa, TV is inside, right? So we recognize the scene categories based on the object inside. So the neural network doing the similar things. So try to recognize this is a bedroom because they see the bed and the cabinet inside, then this is a bedroom. So it means this neural network try to do how human reasoning about this task. Try to discover these object categories before they classify the scene category. So we apply this network dissection for many different architectures, such as the VGG, GoogleNet, ResNet. So we all discover more or less many object detectors, such as we have a lot of this different house detectors and dog detector, train detectors, and plant. It's very interesting to say this architecture have their own preference for the patterns, right? So for the house, like ResNet, like more like a zoom out, this like a European style house, and this like VGG, more like the parts of the house. So they have a different preference for the patterns. So I guess this is related to the architecture designs, also the receptive fields of different units. So we release this policy dissection pipeline at this web link, so you can go there and play with the code and apply to your own neural network you trained. So from that, so I show you that when we train this model for some classification, so there's some concept detector like emerge inside the deep representation, try to help the task. Then we move into the second part, and then we look into the deep representation for image classification. So this task is a little bit different to the classification task, right? So it's more like you given some random latent vector, then it can generate a realistic image. So if you change this latent vector, then this model will give you a totally different image. You change another random vector sample from a random distribution and give you another image. So that is how people use this deep generative representation. But one issue is that giving this kind of data-driven pipeline, you're giving the input, output, but the issue from the perspective point of view is how can we steer the generation process, right? So users sometimes may want different outputs, right? For this given image, they may want a different lighting condition. Maybe they say, oh, I should turn off the light. Also, maybe this person wants a different viewpoint of the image. So giving the current pipeline, it's very difficult to control this process because every latent vectors are just a random vector you sample from the distribution. Also, it's related to what knowledge have been learned inside this latent space associated with different visual concepts such as the lighting condition, also the viewpoint. So then we want to align the latent space of deep generative representation with all kinds of visual concepts we have. That's why we develop a method that try to identify the interpretable concept in the deep generative representation. So with my students, we look into the problem. So we also follow a data-driven approach, giving these pre-trained representations. What we can do is that we can just collect a lot of pre-trained classifiers. You know, in computer vision, we develop all kinds of classifiers. Giving this synthesized image, we can predict the categories, also the scene attributes, or even the layout structure of the output image. Then we can have this outputs, then go back into the inputs and identify the causality relations between the latent code and output attribute space. That's how our framework works. So starting from this initial latent space, so we can generate a lot of latent vectors. So here, each blue dot is a latent vector we sample from some random distribution. Then we can throw this random vector into this trained deep generative representation. So then we can have this image space to get a lot of the realistic battery image. Then we can get into the attribute space by applying some pre-trained classifiers, right? So here we have the classifier that can give us this indoor lighting condition. So we can categorize the synthesized image into this nature lighting and indoor lighting. Then we have this pseudo label for the latent space. Then what we can do is we can go back into the latent space and train some linear discriminative boundaries. Just treat it as predicted labels, as a pseudo label for this latent vectors. So it turns out this binary classification performed quite well. So it can achieve more than 90% accuracy, which means in this latent space, a lot of attributes are already quite disentangled from each other. So after we have this latent boundaries, what we can do is we can do this counterfactual verification using the trained latent vector, the n, just a normal vector, to manipulate this latent code and observe how much the attributes will change. Then we can identify this reliable attribute classifiers. So after we have this boundaries, then we can manipulate this latent code across those boundaries and push their attribute across the boundary. So here is the result we have. Then we can steer the generative model to include more indoor lighting. So here is a demo video. So we have 4 synthesized scene categories. So we have 4 latent vectors, and we push all the latent vector across the indoor lighting boundaries we have in the latent space. Then we can change their attributes realistically. You can see not only this lamp is turned on, also the global lighting condition change very realistically. We also have the not only we can analyze this very beginning latent space. Over the years, people also develop some deep generative representation with this latent-wise or layer-wise latent codes. So instead of putting a latent code at the beginning, so people also have this latent layer-wise latent codes for each one of the layers. So we also can look into their the latent space at each layer and see what have been nerd insights. So we apply our method for this layer-wise latent code. So it turns out there are very interesting hierarchical structure emerge across the layers. So here we have this diagram. The horizontal axis means the layer depth. The deeper is closer to the output image. So we also have the vertical axis is the importance of that layer contributes to some concepts. So you can see the early layer actually controls the layout structure of the scenes, and the middle layer controls the object and attributes. So it shows that the different layers have different specialty to control the generation process. Then we can apply our contributivity, this steerability to each one of the layer and see what will happen. So we apply our manipulation first to the beginning layers. So you can see here at the beginning we have 4 scenes. Then we apply our method to manipulate the beginning layers. Then you can see here we can actually change the layout of the environment. So here we just change their latent code for the beginning image. Then you can see the scenes, the layout of the scenes will change accordingly in a very realistic way. It's more like a change of view of the camera. This is very interesting because when we first train this representations, the training data we have just individual images downloaded from the web. So we don't have this pairwise or this correspondence across images. It's more like in order to synthesize the scenes, the deep representation try to discover this layout or this 3D structure as a very important emergent structure to synthesize the image. We also can apply our method to this intermediate layer. So here another 4 scenes, we can apply our method to that and push the latent code across scene categories. And we can change the category of the scenes from the bedroom into the styling room, right? So the definition of the category also depends on the objects, right? So if you try to change the room type, you will just move out the furnitures and put in those table and the chairs inside, then you can change the category. Somehow this deep representation emerge, have this object synthesizers. So here's another one, also the attributes, right? So not so much green space there, so we try to add more green space. Now we can just push their latent codes across the vegetation boundaries. Then you can see this vegetation, this green space just grow out from the scenes automatically. Also for the first example, you can see this model even smart enough to put a sidewalk on top of the grass so people can walk around. So it really shows that in order to synthesize the image, so a lot of interesting disentangle attributes inside the latent space. And we can manipulate them and have this kind of image edited. So any questions so far? Or we can have questions at the end. Yeah, yeah, feel free to raise questions. So from that, we can see that the semantic hierarchy emerge inside the latent space, correspond to different visual concepts. So that is about the interpretation about the latent space. So you may wonder, how about this convolution filters, right? So what this convolution filters is doing. So we also have some work looking into this deep generative filters and see what they are doing. So we developed some method called GAN dissection that try to correlate this internal unit activation with output semantics. So what we are doing is that we can apply some semantic segmentation model to this synthesized image. Then we can have this semantic mask. Then we can correlate this pixel labels with the activations and see how much those unit activated by this concept. Then we can associate label for that. So after we have this label, then we can identify many object generators emerge from this thing synthesized. More interestingly, we can have this application, this human AI co-creation demos. So basically, we can let users to just brush this image. Then we can identify the units in those activated by this region. Then we can turn on and turn off this unit. Then we can have this different concept included or removed from the image, right? So the user can brush this and include more grass. Then we can include more grass. So here we want to include more trees. So we just activate this tree unit. Then the tree will grow out from that. Also, we want to change the DOM type, add the DOM there. So we can have all kinds of this kind of image editing applications have this human AI co-creation for our content. So the previous work is more about using the trained classifier to discover the internal knowledge. But nowadays, people train all kinds of models on different type of images, such as here is a very cute generative model. People trained on cats, right, for cat generation. So for cats, we don't have so much attributes, so we cannot like annotate a lot of cats, right? So we also want to do this kind of manipulation. So what we can do? So we can also have this unsupervised disentanglement of the deep generative representations. So we developed some works that apply some PCA factorization. So many of you may be the experts in this metric factorization. So given this knowledge representations, so we apply some metric factorization and try to identify those important components into the activations. So we apply this to this knurled deep representations. So it turns out this each component knurl to correspond to different concept. So here we have the slider bar. So each slider bar corresponds to one discovered component. So you can see here user can just drag this slider bar, then we can increase and decrease the intensity of this component. Then you can see the out of the image will have this change accordingly. So even for this cartoon face, so we can drag this out, then we can change even the pose, change the pose of the cartoon characters, and change the mouse size. So this component in order to align with this meaningful concept, even those components are not told to do so, right? So for our training, it's just the image generation training. So we just collect a lot of cartoon character and train this generative model and apply this metric factorization. Then we can identify this meaningful components. Then it can support this human AI share creation interface, allow user to create with this AI model together, change different attributes. So we have some recent works that try to apply this kind of method to even a broader perspective. So here we have this more recent work that developed some method that's unsupervised discovering of steerable factors in the graph model, right? So people have this scientific models as a graph neural network or some graph generative models trained for this molecular generation. So now we can go back into their latent space and discover this meaningful factors or component inside this molecular generative model. So here I show you this 4 meaningful factors as discovered inside this molecular generative model. So they control different attributes for that, like a number of halogens and chance lengths. So then we can manipulate these moleculars and by pushing this latent codes across those different boundaries, then we can generate different moleculars with different attributes. So that gives us more controllable for the generation process. Okay, so that is the second part. So the last part, we'll move into more recent works, that is the deep representation trained for this reinforced learning or local motion task, right? So, reinforced learning is a very popular method nowadays. People use reinforced learning to train AlphaGo, or OpenAI uses reinforced learning to train a lot of this game playing. Basically, it's a trial and error learning process. So we have this agent, so it's also a neural network. We also have the environment, so it's an interactive environment. So the agent tries to maximize the reward it can receive from the environment, then we try to make the decision. So we receive the observation and reward and output the action to the environment. So here we just have a very simple training task. The training objective just move forward. So if the agent can know how to maneuver its legs, then move forward, then get positive rewards. So after some trainings, then we have this agent can move forward very nicely, right? So, but we still have some fundamental questions, right? So it's, first is about interpretability of this reinforcement learning agent. So what have been learned inside this autonomous agent? So why this agent can make this autonomy decision in this uncertain environment is also about the controllability. Like after your training, so if you launch this agent in the environment, then it just work fully autonomously. But we still want to have some controllability over this agent, right? So how to control this agent behavior. So that is a very challenging task. So to address this task, these questions, we have some recent Europe's works that try to look into the deep representation trained for this local motion task. So we develop some method called policy dissection. So from the name, you can see it's an extension of our previous work on network dissection and GAN dissection. Try to look into the deep representation and see what have been learned insights. So we want discovering this actionable knowledge. So what we are doing is that we can have this trained agent, right? So we can generate, because this agent already trains, so we can just run this agent. Then we can collect a lot of observations with different kinematic attributes. It's about the velocity of this agent, also the height, yaw rate. So it's different locomotion attributes or parameters for this agent. So we can collect all those observations as a time series. We also can collect their neural activation time series, right? So what we can do now is just calculate the distance between the two. So because those two sets of signals are time series signals, so we can apply this frequency analysis method to match this time sequence in the frequency domain. Then we can associate these kinematic attributes with internal activations, identify which parts contribute which kinematic attributes. Then we can have the secure-man interface. User can just activate and deactivate this unit. Then we can evoke certain behavior for the agent, such as deceleration or spinning. Like spinning is more like increase the yaw rate of this agent. Also increase hitting directions, and this agent will move up. So after we have this kind of semantic labels for these internal activations, we can have this very cool human-machine teamings. We can associate the keyboard with the internal activations. Then we can control this agent. So you can see here, user right now is press the keys. Then we can more like issue an order to this agent, like move left. Then this agent like start move left. Press another one, this like stop, and stop there, and we're spinning and try to spinning around. Then we can have this controllable agent. So here another environment we explore that we apply this method to another robot that trained for this task. So it's a Bipedal Cassie robot. So you can see this at the beginning, this training task, just doing this like walking forward. So it's a very boring task, right? Just train this bipedal robot jumping forward, so it keep jumping forever. Now we apply this policy dissection to this trained agent. Then we can discover a lot of very interesting motion primitive inside the representations. So here are 6 motion primitives we discovered. You can see there are many interesting primitives, such as this crunch. Then this agent will just lay down and will crunch. And also we even have this backflip. So this backflip is more like combine the jumping and also the horizontal axis movement. Then we can have this backflip. We also have this jump, this turn left, turn right. So after we discover this motion primitive, now we can have this enable this human AI share control. Then you can see here this agent is associated with this keyboard. Then user can press the keys. Then we can activate the behavior, a certain behavior of this agent. This environment is interesting because our training environment is just this moving forward without any obstacles. Then here we just deploy this agent in a totally new environment. So with this domain gap of the training environment, then with the human in the loop, then we can help this agent to overcome this environment. Like here is the bar there, then we can ask the agent to crunch and also press key, then the agent will do this backflip. So it's more like you have a pet dog, so you train this dog to do some tricks. So we can use this for the training. So here we apply this to another environment, to this this 4-legged robot. This training task just moving forward without any obstacles. Then we can apply, if you deploy this agent in a new environment with obstacles, then this agent don't know how to overcome this because there is a clear domain gap between the two. But if we apply the policy dissection there, then have human in the loop to help this agent to solve this testing environment, then we can like issue this high-level order. Then this agent will execute these orders and then overcome this task, this navigation task in this environment with obstacles. So here is this human AI share control environment. Yeah. Yeah. Yeah, so our training task is just to move forward. So after training, this agent can move forward. Then we apply this policy dissection. So policy dissection is more about, so here we collect their attribute. Yeah, so we collect their attribute, like the height and the velocity of this agent. So it's more like observation for this agent. So we also collect their neural activations. Then we can build this correspondence between the two. Then we know which neuron control which kinematic attribute. So after we have that, we have another process that we will randomly activate this certain unit correspond to this kinematic attribute. Then we can have a human to observe what happens inside the representations. Then they will associate label for this motion primitive. Yeah, begin.
Oh, yes, a very interesting talk. So my question is that when you did your probing experiment, I would be surprised that you find specific single neurons. You probably have a group of neurons that correspond to the activation, whatever the meaningful concept. A lot of details, I guess you couldn't talk about. So can you say a little bit more, how do you disentangle?
Yeah, thank you for the question, Bing. So that's a very good and important question. So after we apply the frequency matching, so we actually identify there's a 10% quantile of units correspond to some motion primitives. So in not a single unit, so we identify the top like 10% of units correspond to certain attributes. It's also related to the neural architectures we use. So right now we use this MLP. In reinforcement learning, people prefer just to use very simple this MLP architecture. So it's a vectors. We identify the most important elements or group of elements correspond to the attribute.
And I assume the 10% is trial and error, right? Why not 9% or 8%?
Yeah, that's a threshold you can use. You can use 5% or 10%. It's empirical numbers you can set.
And you find 10% work pretty well for different problems. So for different problem, you probably have to find the right kind of.
We use the same numbers. We use the same number across different architectures or across different environments.
But for the same problem, but if you go to the image problem, if you want to do some action there, I would think that you have to tune the threshold, or the 10% still holds.
Yeah, for the network dissection, because the architecture is different. It's a convolutional network versus MLP. So we may have different numbers for that.
Okay, thank you.
Okay, so we continue. So can have this human AI share control. So it can help us overcome this domain gap. So here we call this test time generalization slow share control. We have the training environment. We train this agent without any obstacles. So if the testing environment with obstacles, then this agent don't know how to overcome that. So we have some quantitative evaluation. So if we directly deploy this agent into the new testing environment, the performers drop very significantly. Then if we have this agent plus human, so have this share control, then we can recover the performance. It's more like we can have this kind of hybrid system to accomplish this new environment that never seen by the agents. Then we can recover the performance. As a baseline here, we just train this agent in the new testing environment, so we can get the numbers. So the number already quite close, which means we can have this share control in testing time to overcome this generalization. So that is actually quite common in real world, right? So in real world, we face this open world. So we want human consistently teach this agent about new concepts, can work with this agent to overcome new domain gap. So that's why I'm very excited about this live work for this human AI collaboration. So we will have this future of human machine collaborations into the future, right? So as we have more AI models and more capable robots, so we don't want this robot like overtake our humankind. So we want human work together with these machines to accomplish different tasks, such as work with this robot arm, or we have this skeleton that we can empower human capabilities. Also help this disabled people to have a more normal life. Okay, so I would like to stop here. So hope through this talk, I can convince you that when you train your models, you should look into this learned representations. So in the deep representations, there are a lot of very interesting, interpretable, and actionable concepts like buried inside the representation. If you can go there and discover, then you probably can discover a brand new applications for your model. Okay, thank you.
Thank you.